do a real quick one just to remind ourselves how fast this can go, especially if we use those relations. Pay attention to what the loading is, what the the constraints are, and things can go really quite quick sometimes with some of these. So, got a simple one here with a couple point loads, one distributed load just to make things nasty. So, we're fine, that doesn't make things all that nasty. Okay, there we go. So, 20 kips, 12 kips there, and 1.5 kip per foot. And then the distances between these 6, 8, 10, and 8. So 6 foot, 8 foot, 10 foot, and then this end piece there, 8 foot. All right, nothing more than we weren't doing last fall. Nothing new here other than just a little bit of warm up. Plus, we're going to speed things up a little bit as we get better at these. Of course, you can determine that these reactions are 18 and 26 respectively. You just do that with your statics. Double check. Remember, to do that, you need to replace the distributed load with an equivalent point load, but then once you've done that, you're done with that equivalent point load. Now, a lot of students will leave that there, and it's not a real load. It's just a convenience, if nothing else, that allows us to actually calculate the reactions. We only put in that equivalent point load for finding the reactions. To find the shear moment diagrams, then we take it out. And we're going to find that the shear moment, especially the moment diagram, the moment diagram gives us a very clear picture of what the beam itself is doing, as we'll see in a couple weeks. But then to finish the shear moment diagrams, we only need to use some of our relations and go quickly through the using the relations to find the points as we go through these. All right, as you remember, for a reaction, an upward reaction here, that's going to cause us to actually go up by that amount. Then nothing happens to the next spot, so it's very easy to do. Most of the shear diagram is actually quite easy. We just take jumps in terms of the size of the point loads, and then nothing else happens until the next point load. So as long as we don't have a distributed load, these are really pretty easy to do. So we took a jump up at 18 for the reaction, a jump down of 20 for the point load, then we take another jump down of 12, so that takes us to minus 14 here, or minus 2 there, and 18 there. And nothing else happens till we hit the next point load. We jump up by 26, so we're at 14, up another 12, puts us about right there. And then we have the, that's right. Yeah, then we have the distributed load that takes us out to a free end. That free end's not going to have any residual shear, so we'll finish at 0. And we can get the shear diagram just that quickly. And remember, take that point load out that we used for the distributed load here, because that does not apply on the shear diagram. I've seen over the years, a lot of students will leave that point load in there and then in some way try to incorporate it in the shear diagram. But that point load doesn't exist. It's not a real load. We need to get back to the real loading that we have, that distributed load there. And then for the shear moment diagram, well, we can look at the loading and realize we've got this pinned end here. Since it's pinned, it's free to rotate. There won't be any moment at that point. We can sort of say the same thing for the other end. It's a free end, so there can't be any moment in the beam when we get to that point. So we know those 2 points exist. Then the rest of it is just a matter of putting little pieces together. We know, remember, that the shear equals the slope of the moment diagram at any place. We've got this positive 18 slope, so we have a positive 18, we've got this positive 18 shear, we've got a positive 18 slope, and the area there will give us the change in M, which is 108. So we go up as high as 108. And we know it's linear down to there. Then we have a very small -2 slope, but it's easier to take the area, find the change then to the next point, and then just connect them with a straight line. And so let's see, we have 2 times 8 is 16, so we come down to 16. That takes us down to about a 92, and then we just connect that with a straight line. Not much easier way to do it than that. Then we have a -14 slope. We know that area is, -14 times 10 is 140. Takes us down to a -48. So that would be right about here, give or take a little bit. Again, connect it with a straight line. And then anytime we have a uniform distributed load, we'll have a straight line on the shear graph and a parabola on the moment graph. So just look at the moment graph. We know we're going to finish at 0. We've got a lot of positive slope, and that positive slope decreases until it hits 0. And the parabolic shape that gives us that is just a simple curve like that, and we're all done. Again, remember what we're paying attention to now, starting today really, is what's the maximum shear and the maximum moment, and in a little bit we'll look at where those are as well, because what we need to do is protect the beam from failure from the maximum shear, which in this case is the 18. It's only for a little section of the beam, but typically we just make the beam uniform all the way across. It's a very cheap, inexpensive way to do it. So we'll protect the beam for this section, but it'll be protected all the way across because that's the worst section. Same thing for the moment. We're going to have to build the beam to protect it for this one spot of greatest moment, which means we're grossly overprotected at other spots, but it may be so cheap to do it that way that that's the preferred method. All the beams in this building, I'm sure, were just stock beams, all uniform in cross-section, probably all match each other. It's just a very cheap way to do it. Don't forget, we don't protect for just that one little spot there. We know where that spot is, know what its value is, and then tack on a big factor of safety anyway. So we don't design for this spot. We design for that spot plus a whole bunch more so that there's virtually no chance of failure. You know from the history books that when buildings fail, they tend to fail catastrophically. So we're going to try to avoid that, especially if you go into structural engineering and you do. So now what we're going to look at is just what do we do to make a beam that is protected for these kind of failures. So this section then, oh my goodness, that's pretty chalk. That's a new color chalk. That's very pretty. Look at her, look, she's smiling. She likes that. So what we're going to do is design for prismatic beams. To start with, we're just going to determine what is it we need to know about the cross-section so that we can do this economically. And then in a little bit, a couple weeks, sometime after break, we're going to actually look at the deformation caused by this. We know these beams bend. We're going to use that today to establish things, but we're not going to quantify the deformation yet. Kind of like we did in the other things we looked at. We look at the loading in the beams, and then we look at their deformation. So first thing, I just need to simply define for you what prismatic means. We're going to look at beams of any cross-sectional shape. Could be circular. You'll see that we can handle virtually any shape. So we're going to let, for the most part, that will be our axial distance, our axial dimension. We'll put x down the length of the longest dimension of the beam. Typically, we'll let y go up, and then using a right-handed coordinate system, z will come out from the side there. So our prismatic beams are those defined such that they are symmetric with respect to, that's what WRT is, symmetric with respect to the y-axis. So if we look at the cross-section, we'll see if we look right at the cross-section, look down the x-axis, there's our y-axis going up, our z-axis coming out. We're going to look at any beam that is symmetric about the y-axis. So any rectangular beam would certainly satisfy that. We could look at triangular or circular beams. But as most of you know, the most common beams in construction are I-beams, and those are symmetric about the y-axis. So they satisfy our definition of prismatic beams. And we could look at any other shape thereof. So that's our first requirement for prismatic beams. Our second requirement is that the moments, all these bending moments in the beam, are exactly as pictured, are in the plus or minus z direction. Which means all of the loads, the transverse loads, if that's what's causing the moment, are in the y direction themselves. Exactly what we've got here. All of these loads are in the y direction. They cause bending that is all in the z direction. Any one of the typical type of loadings we've looked at before. At any place we have bending like that, either plus or minus, depending on what it is we're talking about. What that's going to cause for us is when the beam deforms, when this beam actually bends under these loads, and this one would probably do something like that, greatly exaggerated of course, all of the deflections are in the plus or minus y direction because of these z moments. So that's our whole setup for the design for prismatic beams, and it's now that we're going to actually talk about these cross sections. What do we need in terms of the actual shape and dimensions of the cross sections to help us protect the beam against those moments? And the shear, we just need enough area to avoid shear failure. Here we're going to actually need particular shape because, well, you'll see why in a little bit. All right, that's the setup. Is everybody comfortable with that? Pretty straightforward, pretty simple. We're going to be looking at very regular geometries in this way, at least certainly for the foreseeable future. So let's start the setup and see where this takes us now. Uh-oh, that new chalk is leaving ghostly apparitions. All right. So here's the deal. We have some beam in some kind of loading. I don't care what. We're going to be doing all kinds of different things. That's not the concern here. We can keep it a simple picture to start with. Some kind of central loading that's going to cause some kind of bending like this. I don't care what the specifics are. Just for now, to set things up, I want this kind of curvature. Because what I'm going to do is now take a look at a small piece of that bending, that bent zone, if you will, and really try to set it up. So we'll take a little elemental piece of the bending there and really blow that up so we can take a real good look at it. So we have that sort of trapezoidal region here. Now it's got a little bit of curve on the top, curve on the bottom. So that's our greatly exaggerated piece of the beam there. I hope you appreciate it. It's greatly exaggerated. So that's a prismatic beam here in our typical bending mode that we're going to be looking at. Now, obviously, I hope obviously, the top is being compressed because of this bending, and the bottom is being stretched in tension because of the nature of that bending. In a straight unloaded state, of course, there's no deformation. But now there's some kind of compression at the top, some kind of tension at the bottom. Well, the only way for that to occur is if there's some place in between where we go from the compression on the top to the tension on the bottom, somewhere in between where we have zero load. We'll call that the neutral axis. Neutral axis. I'll just draw it through the middle there and put a little NA on it. Stands for neutral axis. And that's where the load is, actually I don't want to say the load. I want to say that's where the bending is 0. Because we could still have shear there. So the load might not be 0 in its entirety, but we're only looking at the bending right now. So there's some neutral axis. I don't know where yet. I know where. You don't know where yet, where the bending is 0. It's compression on the top, somehow varies to 0 at the neutral axis and then becomes tension on the bottom. It may be linear in between. It might be parabolic in between. It might be a constant compression and all of a sudden a shift to tension. But we've got some place in the neutral axis where we go from compression to tension as we go down through the beam, and we need to find that spot. All right, let's define for us a couple more things. Let's see, let's call this entire angle here, let's call it del theta. That's this angle that we're subtending here with our piece that's delta x in length. Remember, x was the axial dimension. And so we have a little piece delta x here. So that's actually the length of the neutral axis. If the neutral axis has 0 bending, then it's the original delta x in length. And one other thing we're going to need is, at this point, there's some radius of curvature, and I'll call that rho. We can find some at least local center of curvature, and the beam has a radius from that point of a delta r. So there's our setup with that. All right. Everybody comfortable? While we now will take another look much more closely at what's happening there so we can figure out what the deal is. So again, I'll take that picture, I'll blow it up some so we can really see what's going on. Oh, by the way, these spots that were originally planes remain planar. There's no deformation of those, at least not with what we've got going here, because we don't have any axial loading here. So these are still planar surfaces on the edges there. All right, so there's somewhere there is then our neutral axis. We don't know where yet, and we don't know what the distribution is above and below that. But we're going to use that. That's very important to us. That's got a length delta x long because it's undeformed. It's bent, but it's not compressed or in tension like all of the other parts of the beam are. So we're going to measure our coordinate distance y from there. Remember, y goes vertically across the cross-section, so we're going to measure it from the neutral axis up to some other surface. So that's my positive y direction. That takes me up to some other surface that I'll call delta x prime in length. It's compressed as I've drawn it. It's a little bit shorter, and it's a distance y from this unknown neutral axis. All right, what else are we going to need here? Radius of curvature of rho down to the neutral axis. So down to this intermediate axis of some kind, the radius of curvature is rho minus y. And as you imagine, we're going to vary y across the entire cross-section. and see where we get. So that's our geometric setup there as we take a look at all parts of it as we go across. Comfortable with that, John? Or just have a last day before spring break headache? Okay. So let's see. Let's look at the normal strain. Remember, the normal strain defined as some deformation over the original length. That's just the original, our original definition of the normal strain. For us here, it's going to be, let's see, the deformation is delta x prime minus delta x over, oops, leave a little space after the equal sign. Delta x prime minus delta x over delta x, because that was the original length of my little section here. But I'm going to take the limit of that as delta theta goes to 0. And that will, what I've got is, without that limit, I have a rather macroscopic strain, but I don't have the instantaneous strain, if you will. All right, so let's see what happens with that. Okay, delta x prime, that's the arc length of the radius times the angle. That's delta x prime. Agreed? That's just arc length. Delta x, or delta theta, of course, being in radians, minus delta x, which is rho delta theta, and that's all over rho delta theta. Okay, delta theta cancels. We have a rho minus rho left over on the top. So rho cancels. We don't even need the limit anymore because delta theta canceled. So we get the rho's cancel. We get minus y over rho. That's pretty simple. That's pretty simple. That's by golly, that's a linear distribution of the strain across the cross section. That couldn't be any much more simpler for us. And of course, in terms of the normal stress, then, which is related to the strain by Young's modulus, we can then take out the strain, replace it with minus 1 over rho. And so we even have a distribution, and we even see it's linear for the stress as well. Which means if we look at some beam under some kind of loading, we know there's some neutral axis somewhere. We don't know where yet. And we know that, at least for this type of bending, that we have compression that varies linearly on the top, and tension that also varies linearly on the bottom. So that's one way we could draw that distribution. The only trouble is we just don't know where the neutral axis is yet. But, much to our relief, couldn't be much simpler than linear. So for the bending shown, we have linear varying compression on the top half of the, well, top, I say half in quotes because I don't know where this neutral axis is yet. That's our next job. We can also say then, of course, that at the extremes, the maximum strain is at this very top surface up here, and that's not at Y, but that's at C. Remember, C is our convention for the maximum distance. It was always maximum distance from wherever our coordinate origin direction was, but now it's going to be from the neutral axis. We don't know where it is yet, but we're going to place that in a second. And of course, we can also say the same thing for the maximum stress. It also varies linearly in the same way. So those are two pretty useful things. Combine that with the fact that it linearly varies in between. So once we determine where in the world this neutral axis is, we're going to be cooking with gas, as we say. Yeah, those deserve a box, don't they? You betcha. Okay, so we need to figure out where that neutral axis is. So that's the task, our current task now. All right, so we have to figure out what this neutral axis is. So we have some beam like this with this unlocated neutral axis with this linear variation, and we need to find this neutral axis. It's a statics class, so the first thing we need to guarantee is that the forces sum to 0. Because there's compression above and tension below, we need to make sure that those two things balance each other, that we have no residual forces left over, because if we do, we have then acceleration, not in this class. So we're going to make sure that the stress over the area will then be 0. So that's actually the sum of the forces, because the stress is the force over the area, and that now needs to be 0 as we integrate over the area. But remember, the cross-sectional area. Okay, so let's see, what can we put together now? Let's take that then. Now this sigma x, we know it varies linearly from 0 to sigma max at the extreme. So we're going to put that in for sigma x, the local strain. That's going to vary linearly between the maximum, no, not y, c, because we're using the maximum. Make sure I get this right. No, the y was okay. The rho is not. We want to be at c. Yeah, rho cancels out. We get just c in there. Actually, rho doesn't even have a part of it. All we're doing is setting up this linear variation, dA. Yeah, okay, that's what I need. Now, here's the beauty of this, and how we start getting to the answer. That is a constant. It doesn't vary anywhere in the cross-section, because that's the maximum stress at the outer limit of the beam. That doesn't vary. Neither does C, so we can bring those out of the integration. And we're just integrating then y dA, again, over the entire area. Yeah, that looks good. And that's got to equal 0, because that, remember, is the sum of the forces. Most of you should be tingling with anticipation at what's there. Tommy? Are you? Because this should look very familiar. What is that? David?
Let me think here. Something having to do with polar moment of inertia?
Well, not polar. Polar has to do with circular cross-sections. Okay. This is any kind of cross-section. If we have a circular cross-section, that would be. But this is the first moment of area.
Okay.
It's hard to write down here. First moment of area. Is that pretty funny? Okay, take notes exactly like I wrote. You come up here and try to write down here in the bottom. Sailor's having a fit. Okay. First moment of area. That's great because that's what we've been figuring for some time. We did that back in statics. So let's look at that a little bit and see what that means to us. If you remember, we had to find this spot y bar, which was the location of the centroid of area. And that was defined as the integral of y dA, exactly what we've got there, over the integral of dA itself. That just came from this being over here, so that we had essentially a y integral dA equals integral y dA. We were finding this location of the centroid, essentially the balance point of the area. Now, we just got that, which means that this part there equals 0. That's what we just established over here when we summed the forces to 0. This all means then that our neutral axis passes through the centroid of the cross-section. Which we know how to find. We spent some time doing that in the fall. We'll review it real quick today. But that allows us to place this neutral axis, and we now can establish the distribution of the stresses across the cross-section. So that's pretty useful to us. Again, deserving of a pink box there. Because we know how to find the centroid. For a lot of very regular cross sections, like just a simple rectangular beam, we don't have to calculate anything. We know where it is. If we have a beam that's symmetric not only about the y, but also about the z, we immediately know where this cross section is, or sorry, the centroid is. So it makes things quite simple. All right, so that's our first static requirement for this class. Remember, this is a class in statics itself. The second is that the moments must also sum to 0. So we're going to integrate some moment arm times the force, but we've already got that, so that's sigma x dA. That's dF. So that's h little force times its moment arm. And that's going to be equal to the moment across the whole piece. All right, let's make the same jump we made before when we put this in for sigma x. So this becomes y sigma x gets replaced by sigma max times y over c. Oh, yeah, and the minus sign always pull out. I may have produced or lost a minus sign earlier. Well, it's going to turn out it doesn't really matter because we know exactly what the directions are anyway. So the tradition is the minus sign and a little bit's even left off. Again, minus sigma x, sigma max over c is a constant, comes out of the integral. We're left with, oh, sorry, dA. We're left with y squared dA. Which again should look familiar. This is the second moment of inertia, or that which we typically just call capital I. And we've got lots of those in the book there. And that's with respect to the neutral axis. So that's the moment of inertia as calculated from the neutral axis. And we're going to have some compound shapes, so we're going to need all that little bit there as we put things together. So, boy, that tidies these things up. We get that the maximum stress is minus mc over I. And the equivalent, the local stress is minus my. So because the stress varies linearly in between. What we typically do now is don't even use this, we write this down without even the minus sign being there because it's so obvious from the bending whether that's compressive stress or tensile stress because of the way these beams bend. It'll be compression above and tension below for that kind of bending, and if we have bending in the other direction, then we have tension above and compression below. With it being 0 at the neutral axis. Oops, two different ways to draw those very same things. Well, you get the idea. You can tell from observation what kind of stresses you've got, whether it's compression or tension. But the biggest revelation with this is that the smaller the moment of inertia, the greater the normal stresses. As I goes down, the stresses go up and vice versa. What that means to us and our experience is that an I-beam in cross-section has a lot of area. The neutral axis, because of the symmetry, we know it's going to go right through the center. There's a lot of area for an I-beam that's away from the neutral axis, which means for the same cross-sectional area, which we need to resist shear, we have the same area, but we have a much greater moment of inertia with an I-beam because of this additional area away from the neutral axis, as we'll remind ourselves here shortly, doing another calculation of finding this. This greatly increases the moment of inertia. Gives a greater I and a lower normal stress. So that's why we use I-beams in construction. We could have done a rectangular beam, but those are very heavy. This is much lighter, with a relatively greater moment of inertia. So that's very, very useful to use I-beams. So, real quick calculation with it. We'll keep it simple for this first one. We'll just use a beam in rectangular cross-section. Exactly what you'd use if you were building a deck this summer. You would use 2x8s for the joists, maybe just 2x6s depending, and you'd orient them in that way. So for so find the maximum moment that causes yielding. In other words, the design normal stress we're looking for is the yield stress. That's the type of thing that's in the back of the book for different materials. And we want to find what moment keeps us at or under that yield stress. So, a couple values to use just to run through the calculation. We'll assume a yield stress of 36 KSI. Because of the symmetry, we know the neutral axis goes right through the center, and we'll give it a dimension of 1.25 inches that way, and this dimension 0.8 of an inch there. Then we want to find for this real quick example, what's the maximum moment we can withstand with that, and we just have to calculate those. Just a quick run through as we do these. Gotta watch the units, of course. Yield stress I gave you is 36 KSI. C I gave you, that's 1.25 inches. We just need I for a nice rectangle, which is, who will integrate that for me? Well, no one will. Nice rectangular shapes, remember, like this, they're in the book, so you just have to look them up. This one happens to be 1/12 BH cubed, where B is the base and H is the height. Make sure you get that right when you look at the pictures of those in those tables in the book. So the beam has a width of 0.8 inches, a height of not 1.25 but twice that, 2.5 inches, and that's cubed. And so we've got I, we can put that in there. Simple as that. Couldn't be a whole lot easier. Units okay? Kips per square inch takes off 2 of the inches to the 4th. We've got another one on the bottom. We're left with kip inches, which is a good unit for moment. Kip inches. All right. Just a quick refresher. Most of this, well, all of the shapes we're going to need are available in the tables in the book. What we're going to have to do, though, is we're going to have to look at a lot of compound areas, because if you look in the book for the tables of moments of inertia, the I-beam's not there. Neither are a lot of the other types of shape. It's pretty common to use built-up box beams, especially when you're working with wood. It's a really cheap way to get a lot of moment of inertia, as well as a nice aesthetic look. When you have these, it looks like big solid beams, but they're really just built-up beams and cross-section. It's not uncommon, too. You might want to run some kind of pipes or wires or something down those beams just to make the house look a little cleaner in appearance. So let's review then how to find the neutral axis and the moment of inertia with respect to that neutral axis for some non-standard shapes, some built-up shapes. All right, so let's look at a beam like this. Very simple to start. Nice long beam with a single point load at the center. 4 kilonewtons on a 5 meter beam, so the maximum moments at the center. And for whatever reason, let's use a cross section that looks like this. And then we have to figure out what the maximum anticipated stresses are. So for whatever reason, the cross section looks like that, an inverted T. Maybe maybe they were gonna put toy railroad that runs around there. I think that was it. That'd be fun. I'd live in a house that looks like that. All right, so in millimeters, the dimensions are, that little piece there is 10 millimeters wide and 150 millimeters high. The bottom piece is 15 millimeters by 120. But it is symmetric about the y-axis as our requirement for the built-up beams. All right, so we need to do two things. First, we need to find where the neutral axis is. Because the moment of inertia we calculate is with respect to that. And if we don't know where it is, we can't calculate the moment of inertia. So we need to find I with respect to that neutral axis. All right, so here's what we do. First step. We just pick some reference location from which we measure everything. That will allow us to find y bar that defines the neutral axis, and once we know where that is, we pin it to the cross section. We don't need this reference position anymore. So I'll pick a reference position. I don't know, what did I pick? Oh, it's right there. So I'll pick, it's arbitrary, I'll pick a reference position at the bottom of the beam, and I'll just measure everything from there. That will allow me to figure out where y bar is. In our experience, we know it's going to be someplace like that. Once I've found out where that is, it's a part of the cross-section itself, and I don't need that reference position anymore. It's just a convenience for us to quickly establish where the reference position is. So, pick a reference line, just a place from where to measure things until we find out what y bar is. And then 2, calculate the moment of inertia with respect to that, reference. Okay. All right, one easy way to do that is to break these into pieces. So I'll call this piece piece 1 up here, and this piece 2 there. There's different ways you can do it, but they should all come out in the same way. And then make a table out of that. So I have 2 parts, 1 and 2, and I'm going to need to find the quantity there. If you remember, that's the kind of thing we had to do to figure out where the centroid of a compound area is. So I'm going to need the area of each of those pieces plus the location of the individual centroids of those individual pieces. So the areas are easy. Area 1 is 10 by 150, 1,500 millimeters squared. Area 2 is 15 by 120, which is 1,800. That's just looking at the chart, figuring out what these individual areas are right off the table. And then I'm going to need the sum of those areas for the denominator. So what is that? 3,300 square millimeters. That there, as easy could be, is my denominator. Now I need the location of the individual centroids with respect to my reference line. So 1 is, let's see, it's a distance of 15 up and then halfway up itself. So what's that? That's 15 plus 75. Is that right? That's the location of Y1 from my reference line, which was just a matter of convenience. Could have picked it anywhere, doesn't matter. We're just looking for the neutral location so we can then be done with that reference thing. So what is that? That's 90? Agreed? Everybody see that? What then is Y2? There's a guess. What do the others say? We're looking for the centroid. This is the location of the centroid of the second piece with respect to my reference line. Due to its regularity, we know that to be right there in the center. It's at 7.5 millimeters. Now, we don't need those summed up, but we need that times the area summed up. So that's pretty easy to figure out in the next column of the table. This one's 135,000, and that's millimeters cubed. 90 times 1,500, 135,000. And the other one's 13,500. And those we need added up because that's the numerator. And then we can figure out where Y bar is. So those add up to 148.5 millimeters cubed. So now we can do this. 148.5 millimeters cubed over the sum of the areas, 3,300. The units work out? Yeah, we're looking for the distance of the centroid of this compound area from our reference axis. Once we've got that, it places it on the cross section, and we don't need the reference position anymore. It was just an artificial convenience to find all this part of it, but then we're done with it. And that is 45. 45 millimeters. And look at your solid and make sure that that makes some kind of sense. We've got this piece here, that piece there. Just by simple observation, we'd expect it to be somewhere in there. If we had this piece cut out of cardboard, that's where we'd expect it to balance. And by golly, doesn't 45 look pretty darn appropriate? Measured from our arbitrarily chosen reference line, which we don't need anymore, because now we know where the neutral axis is. So we know that this beam, when bent by that 5 kilonewton load, 4 kilonewtons, we know that the beam, we know the distribution. So if we look at the beam in cross section, there's that bottom plate. And we know that 45 millimeters up from the bottom, is this neutral axis, and that our stress distribution is linear about that. We'll have compression along the top because of that type of bending, and tension along the bottom. And in fact, we can even figure out how much now. Because we have all of these pieces. But let's make sure we've got them right. What's the maximum moment for a beam with this kind of simple load right down the center? It's what? It's actually 4 times the distance to that. It's going to have maximum moment right in the center. As you'd expect, if you were standing on a board like this, you'd expect it to break in the middle, right where you're standing. So it's 4 times 2.5, half the distance, which is 10 kilonewton meters. What's C? What's C? Remember, our convention is that's the maximum distance of beam material in the cross-section away from where? The neutral axis. So C is going to be that distance because that's the greater distance away from the neutral axis. So there's greater stress at the top of this beam than there is at the bottom. Let's see, what is that? We got 15, we got 165 minus 45, so that's 120 millimeters. As usual, we've got to watch the units. And then we didn't figure out the moment of inertia, did we? We got too excited here. We didn't figure out the moment of inertia. Where do I want to do that? We got the neutral axis, but then we didn't figure out the moment of inertia with respect to that neutral axis. And it says so right there, calculate I. I just didn't even read it. Okay. It's pretty easy to do that in the same way using the same kind of table that we used before. When we have a compound solid, it's the sum of the moments of inertia with respect to the neutral axis. So we've got, make a table again, it's pretty easy to do that. The thing is now, we're going to have to use the parallel axis theorem because none of these pieces are lying with their centroids right on the neutral axis. So we'll have to figure out their individual moments of inertia. Then we'll need to find a di for the parallel axis theorem, which you probably remember as the centroidal moment of inertia times or plus AD squared, which is the parallel axis theorem being applied. So we just have 2 rectangular solids. We figure out their own centroidal moments of inertia. That's the values right out of the book, just using the calculations there. So you can double check these. 2,812,500 millimeters to the fourth. Very big number just because we're using millimeters. Remember, that's right out of the book, just using, for these rectangular shapes, 1/12 BH cubed. This one's 33,750. Now, we don't need that summed up. We need to sum up the moments of inertia with respect to the neutral axis. So that's all the way down to there that we're working. The areas, we already had those on the other table, so we don't actually need to refigure those, but we do need to figure out what D is. D is the location of the centroid for the individual piece with respect to the neutral axis. So for piece 1, it's that distance. Nice rectangular piece, has its centroid right at the center, but we're trying to figure out the parallel axis there and the distance we are from that center. Remember, we're up 45 here, which puts us 30 in. We need to go to 75, so that's 45. Sound right? And that's millimeters. And so now I can do I plus AD squared to get the moment of inertia of that upper piece with respect to that neutral axis that we placed. Comes out to be 5,580,000, and this is millimeters cubed. Oh, sorry, this is millimeters to the fourth. Oh, yeah, it is. Wait, yeah, this one's the fourth. This was right. That should be the fourth. Millimeters to the fourth. And you can double check these numbers when you get home. The location of the centroid of the second piece with respect to the neutral axis. The neutral axis is here. The centroid of the second piece is right in the middle of it. That distance is D2. So we're 45 up, and we come back 7.5, so that's at 37.5. Don't round off too much on these. You can at the end, but not too much as you go through these. 2, 5. So this is 2,531,250, and that's what we add up to get the moment of inertia of the entire piece. 8,415. 8,415,000 millimeters to the fourth. And that's what we put under here. Let's see, units work out? In general, you're going to have to watch meters and millimeters, but the units work out in general. Yeah, we've got 2 length on the top, 4 on the bottom, so if we lose 2 of those, we're going to get kilonewtons per meter squared when we fix it, which is kilopascals, so it's going to be all right. And so now, once you watch all those units, you can fix that, and we've got the whole piece. Comes out to be 71.3 megapascals in compression. And the bottom, I think, comes out to be, what is that? Oh, that's just the compression, the value of 2 points we don't need. Which, if this is wood, it would explain why they use this cross-section of a beam. Wood is very good in compression, so you don't necessarily need very much wood at the top. It's not very good at tension, so you're going to need a lot more material down there for the wood to resist the tension at the bottom. A number which I don't happen to have. But now we can draw in cross-section our distribution of the stress. We know the neutral axis to be at 45 millimeters up from the bottom. Just happened to be where we picked our reference. And the top is in compression, the bottom in tension. And we know the maximum stress to be 71.3 megapascals compression at the top. Travis, you're frowning.
For some reason, my answer is double that.
Double what? Double this?
Yeah.
Let's make sure we got the right numbers in. 10 was the, what was that? That was the moment. I have 5 written down there. Why do I have 5?
I think the addition was wrong.
This addition?
Yeah.
Yeah, but it's not going to be perfectly a factor of 2, so there's something else wrong.
If you have 5, that's why mine's double, because I used that.
Oh, okay, it is, yeah, it is 5, because that's the, if we drew the shear moment diagram, we get a shear up of 2, only half of that, and then down to 2. So there's the shear, and then the moment is 2 times 5, only goes up to 10. So that's why we got the half. That this was wrong. This should be 5. Danger of doing things on the fly. And then what, the addition was wrong by a lot or a little bit?
Well, I think when you wrote the first 5 early number, you said 585, and then you wrote 558. I don't know.
Could be, that's easy to do. Wait, 5, oh yeah, this is 8.5, sorry. That better? That probably fixes it, so, thanks, sorry about that. All right, make yourself nice diagrams that are real clear. Don't make them too small, they get crowded. Do these tables. You don't have to, I just find it's an awful lot easier to do the tables to keep all these things straight so that I get all the pieces, especially since I had to use a couple things from the first table, I didn't want to redo them. You get the really big numbers when you do it in millimeters, so you might want to go to meters before, but then that makes some of the other numbers a bit smaller, so personal preference, just as long as you watch your units and you are consistent with them. Okay, so I think that takes us into spring break.